This video is for section 6.3, periodic trends. The learning goals are to understand trends in atomic size, ion size, first ionization energy, and electronegativity. And another learning goal is to understand how ions form. Let's take some notes on that first learning goal. Understand trends in atomic size. Atoms are different sizes. In the periodic table, where are the smallest atoms located? Where are the largest atoms located? And are there any trends or patterns within the periodic table that we can use to predict relative sizes of atoms? With respect to atomic size, here are some general trends. Atoms get smaller across a period, and atoms get larger down a group. Let's take a look at a periodic table. One trend in the size of atoms is that atoms get smaller across a period. Let's focus in on one of the rows from this table. We'll use period 4 as our example. If atoms get smaller across a period, that means that capital K, potassium, is the largest atom in period 4. Potassium is a little bit larger than an atom of calcium, which is a little larger than an atom of scandium, which is a little larger than an atom of titanium, and so on, moving to the right across the period. What is the reason that atoms get smaller as you move to the right across the period? That reasoning is provided in this box. Each atom has one more positively charged proton than the previous element in the row. Greater positive charge attracts the surrounding electrons in closer to the nucleus, resulting in a smaller sized atom. For example, calcium has one more proton in its nucleus than does potassium. That greater positive charge will attract the electrons in a little bit tighter, making calcium a smaller sized atom than the potassium atom. Now let's focus in on a group. Let's focus in on group 1. The trend is atoms get larger moving down the group. This means that within group 1, hydrogen is the smallest atom. Lithium is a little larger, sodium is a little bit larger, and so on, moving down the column. What is the reason that atoms get larger as you move down the column? That reasoning is provided in this box. Each atom has one more energy level containing electrons than the previous element in the column. An additional layer of electrons results in a larger sized atom. For example, hydrogen has only one energy level, but lithium has two energy levels. The extra layer of electrons in lithium makes it larger than an atom of hydrogen. Our next learning goal is to understand how ions form. The concept of an ion is very important to chemistry. We had previously seen the word ion when we looked at metals and nonmetals. Metals are elements that tend to form positively charged ions, and nonmetals are elements that tend to form negatively charged ions. Well, what's an ion? An ion is an atom or group of atoms that has a positive or negative charge because it does not have equal numbers of protons and electrons. There are two types of ions. The first is a cation. This is a positively charged ion. A cation is formed when an atom loses one or more valence electrons, resulting in a particle that has more protons than electrons. Protons are the positively charged particles. Electrons are the negatively charged particles. If there are more of the positively charged than the negatively charged particles, then the atom will have a positive charge, and it is called a cation. An anion is a negatively charged ion. An anion is formed when an atom gains one or more valence electrons, resulting in a particle that has more electrons than protons. Electrons are the negatively charged particles. Protons are the positive ones. If there are more of the negative than the positive, then the atom has a negative charge. So that you don't confuse which word is the positively charged ions and which is the negatively charged ions, come up with a mental reminder that helps you know which is which. For instance, here's a positive symbol. Notice that the positive symbol is like the letter T in cat. Or notice how the word anion has an N right there, and N is the beginning letter of negative. These definitions refer to valence electrons. Valence electrons are electrons in the atom's highest energy level. If an atom is going to gain additional electrons, then those electrons will be gained in the highest or outer energy level. If an atom is going to lose some electrons, those electrons would be lost from its highest or outer energy level. For our next learning goal, let's go back to looking at some trends. Specifically, let's look at trends in the size of ions, first ionization energy, and electronegativity. Here are the trends for the size of ions. Let's first look at cations. Cations get smaller across a period and larger down a group. The trend for anions is the same. Anions get smaller across a period and larger down a group. The reasoning for these trends is identical to the reasoning that we used for the size of atoms. Within a period or row of elements, as you move to the right, the atoms have increased positive charge in the nucleus, pulling in the surrounding electrons closer, creating a smaller sized particle. As you move down a column or group, there is an extra level of electrons, creating larger sized ions. The next vocabulary concept is ionization energy. This is the amount of energy needed for an electron to overcome the attraction of an atom's nucleus so that it can leave the atom. Recall how cations are formed. Cations are positive ions formed when an atom has lost some of its valence electrons. Well, how would an atom lose electrons? Electrons are lost when the electrons have enough kinetic energy that they're moving around so fast that they can escape from the positive pull of the nucleus. First ionization energy is the amount of energy needed for an atom to lose its first valence electron. Second ionization energy is the amount of energy needed for an atom to lose a second valence electron. And here are the trends for first ionization energy. The energy increases across a period and decreases down a group. Let's take a look at the periodic table again. And let's focus in on period 4. The trend is that the first ionization energy increases as you move to the right across that row. That means that potassium has the lowest first ionization energy of any element in period 4. Calcium's first ionization energy is a little bit greater than potassium's. As you move further to the right, over to the area of the table that contains the nonmetals, those elements have very large first ionization energies. Often they're so large that the electrons are not going to be able to escape from the atom. Therefore, these elements do not form positively charged cations. The reason for that trend is shown in the box. Each atom has one more positively charged proton than the previous element in the row. Greater positive charge more strongly attracts the surrounding electrons, making it more difficult for an electron to escape from the atom. An electron needs more kinetic energy to overcome the attraction of the nucleus. For example, calcium has one more proton in the nucleus than does potassium. That greater positive charge attracts the surrounding electrons in stronger than does the positive charge in potassium. It's harder for those electrons to escape. So it takes more energy for an electron to escape from a calcium atom than it does from potassium. The other trend is that first ionization energy decreases down a group. Let's look at group 1 as our example. Hydrogen has the largest first ionization energy of any element in group 1. The first ionization energy for lithium is a little bit less than that for hydrogen. Francium has the smallest first ionization energy of any element in group 1. It takes a lot less energy, meaning it's easier for francium to lose an electron than the elements above francium. The reason is shown in the box. Each atom has one more energy level containing electrons than the previous element in the column. Valence electrons will be farther from the positively charged nucleus, which weakens the attractive force to the nucleus. An electron requires less kinetic energy to overcome the attraction of the nucleus. Our last vocabulary word is electronegativity. This is the ability of an atom to attract a nearby electron. Atoms with a small electronegativity value have a very hard time attracting additional electrons. Atoms with a large electronegativity value have a much easier time attracting nearby electrons. If an atom cannot attract electrons, it's not going to form a negatively charged anion. However, if atoms easily attract surrounding electrons, then they tend to form negatively charged anions. The trends are that electronegativity increases across a period, and it decreases down a group. Let's take a look at the periodic table again. And again, we'll focus in on period 4. The trend in electronegativity is that it increases across a period. That means that capital K, potassium, has the lowest electronegativity value of any of the elements in period 4. As you move to the right, the electronegativity increases. These nonmetals have much larger electronegativity values than do the metals over on this side. These three elements have a much greater tendency to attract electrons than do these elements. Krypton is even farther to the right than these three elements. However, the electronegativity value of krypton is 0. Do you know why? It's because krypton is a noble gas. A noble gas has no tendency to attract additional electrons. The reasoning for this trend is given in the box. Each atom has one more positively charged proton than the previous element in the row. Greater positive charge more strongly attracts nearby electrons. Electronegativity decreases down a group. In group 1, hydrogen has the greatest electronegativity, and then the value decreases as you move down the column. Francium has the smallest electronegativity value of any element on the whole periodic table. Francium has very little ability to attract additional electrons. An atom of francium doesn't want to attract any additional electrons. Instead, francium is likely to lose an electron to form a cation. The reasoning for the trend is shown in the box. Each atom has one more energy level containing electrons than the previous element in the column. Electrons within these levels shield the positively charged nucleus from any nearby electrons, reducing the ability of the nucleus to attract those electrons. For example, an atom of francium has a lot of electrons, 7 levels worth. All those layers of electrons block the positively charged nucleus from being able to influence additional electrons. This concludes the video about trends in properties of elements on the periodic table. We examined trends in the size of atoms and size of ions, trends in first ionization energy, and trends in electronegativity.